Okay, so let's apply this to a few things. We've actually seen ones like this before, so it's kind of not new, but now that we've talked about these domains and ranges, it'll kind of come into more context. So, for example, if I want to solve cosine x equals negative 0.3, again, we've kind of learned to think this through before. Negative 0.3 maybe is about right there, right? So I'm really looking for this point on the unit circle, and whatever that angle is going to be my angle x, right? And if you actually apply the cosine inverse, we can see x equals the cosine inverse of negative 0.3. And when I did that here, I'm using degrees, which is fine. I got about 107.5 degrees. So that's equal to 107.5 degrees. And you'll notice, when I plug cosine inverse of something in, my calculator only spits out one thing. It's because your calculator requires it to be one-to-one. It can't really work very well to say, okay, it could be this or this, if you get what I mean. We know, though, that there are actually two locations on the unit circle that have that same cosine value, right? The other one would be down here. And if I mark that out right there, right, we can see the easiest way to get that full angle would be this full angle right here, right, would be to take this 107.5, remember that that's this much, away from 360. So for me to actually finish solving, I can't just stop there because I'm missing some of it, right? And that's just because cosine inverse is only looking on 0 to pi, because that's what we decided was his range, right? So then we say, okay, then 360 minus 107.5 is going to give me the other solution. So 360 minus my answer, and that's about 252.5. Okay? So this brings more context into this. Now, if I wanted to solve this other one, same deal. We've seen this before. I did it before in our examples. Unit circles 1, so tangent equaling 2 means we're looking for the angle that makes this tangent line, yeah, that's about 2 units in length. So wherever this ends up meeting is going to be the angle that I'm looking for, okay? So if I get that down there, about right there is what I'm looking for. Now, we also know that there's going to be a matching angle down. If I let this continue on to the other side, that is also going to have that same tangent. So I'm going to actually have that angle be included as well. So if we do tangent inverse of 2, we're going to get about 63.4 degrees. So right here, 63.4 degrees, but then I want to go around 180 degrees from there, so I'll just add 180 to that, and I get about 243. So let's do x equals tangent inverse of 2, and that was about 63.4, but then because tangent always has an opposite there, we can add 180, and the other one is going to be 180 plus 63.4, which is 243.4. So my two solutions there, and my two solutions here, and we used what we were thinking about. Our calculator thinks one-to-one, right? But then we have to do the reasoning to finish it off. Okay, in general, it's also good to be able to evaluate, meaning plug in values to an inverse trig function, right? We do need to make sure that it is a possible one. I've given you ones right here that are all possible, but if I said, remember the domain is just from -1 to 1. What if I said find sine inverse of 2? Well, that's not even in the domain, but we kind of, we realize that, right? And that's just because it's outside of sine's range, right? So the inverses and the regular functions really act hand in hand with each other. So one kind of sentence that I want you to think about anytime you're thinking, okay, sine inverse root 2 over 2. Remember, you generally aren't going to see things with pi in them here or degrees in here because that doesn't make sense. You don't put a radian measure or degree into an inverse because that's what's coming out. Don't forget the inverses swap the role of the domain and range, right? So we're saying this kind of question. Find the angle whose sine, cosine, or tangent is blank. So this is saying figure out the angle whose sine is root 2 over 2. So what comes out of this is an angle, right? Again, it's because we swapped the roles of the domain and range. So, the sine inverse of root 2 over 2, go ahead and do that for yourself real quick. You should have gotten 45 degrees, or in radians, pi over 4. Cosine inverse of negative 1. Again, find the angle whose cosine is negative 1. Go ahead. Cosine inverse of negative 1 is 180 degrees, or pi radians if you're using radians, right? And, these are trickier. If I want to figure out the tangent inverse, because remember, to calculate tangent, you actually have to do the ratio of sine to cosine. So we have to think, when is sine and cosine? In fact, I'm going to make this more interesting, because I think we already did one that has this solution. Let's actually make this negative 1. Kind of like that one, but way different in how we reason it. What's going to have a sine over cosine ratio that makes negative 1? Well, to make negative 1, that means the top and bottom of the ratio must be equal, right? Except one's positive and one's negative. Am I right? So it seems like 45 degrees would be good because they're both root 2 over 2, and that would make 1. But it has to be the version of that that's in a different quadrant, right? So on my unit circle, I guess I should have drawn that. On my unit circle, it can't be here, because tangent is going to be equal to 1. So here, halfway between, or else here, halfway between. But which one is it? We have to remember what we came up with here, right? It's only defined from negative pi halves to pi halves when we cut it, which is over here. So actually this whole thing, when I'm evaluating tangent inverse, basically can be ignored, right? So what angle is that? That is the angle that goes all the way around and then 45 degrees more here. I know that doesn't look like 45 degrees. So this is going to be 270 plus 45, which is going to be 315 degrees, I believe. So this would give me 300. Actually, no, I made a mistake. I don't know, maybe I'll keep this in the video. Mistakes are good. Actually, that puts it all the way around. Remember we said we don't allow that? I don't even know why I was thinking that. I need to actually, if I plug this in, it's going to spit out the negative version of this angle. I'll keep this in the video because I think that's a good thing for you to accidentally make the mistake of, because me, even still, it's easy to make that mistake. It has to either be negative pi over 2 to positive pi over 2, or negative 90 to positive 90. So actually it's easier than what I just did. You can just say it's a negative 45 degree angle. And if you put that in your calculator, you'd get the same thing out. You'd get negative 45 degrees. Okay? So it's a little weird how that works and how those things spit those different things out. Because when we're solving equations or evaluating things, we're normally thinking in the positive angles, right? 0 to 2 pi, like we have been. But in these cases, based on how we restricted it, it's only certain things we keep. But this still is able to be evaluated, but the actual answer is negative 45 degrees. To finally wrap up the last 3 pieces of this example here, you'll notice that we have a composition, right? We've actually put a function within a function. And this is kind of weird because we're normally used to, when you compose 2 inverse functions, remember one of the major facts about inverse functions is that when you compose a function with its inverse, they essentially just cancel out, poof, and you're just left with whatever was inside. So you might think, okay, cosine and cosine inverse, bam, bam, cancels out. You're just going to have root 3 over 2 come out. Totally makes sense. So let's actually evaluate this and make sure that works. The cosine inverse of root 3 over 2, remember that's just asking what angle has a cosine of root 3 over 2. Well, if we think about cosine being root 3 over 2, that's going to be, looking on your unit circle, pi over 6. I'm going to work in radians to finish these examples off. So what this becomes is the cosine of pi over 6. Am I right? Well, the cosine of pi over 6 is, well, root 3 over 2. So it worked out exactly like we thought, right? These are inverses, so poof, they cancel out, yeah? But we have to be careful when we're going the other direction. Meaning, when I'm taking the inverse of the sine of whatever. You see how these are different? This had the inverse on the inside. This has the regular sign on the inside. Because watch what happens here. And it's because of the altering we made of the domain and range. for sine inverse. Sine of 11 pi over 6, that's going to be all the way in the fourth quadrant. And that's going to give me a sine value of -1/2. So this becomes sine inverse of -1/2. But you know that 11 pi over 6 is not going to be what comes out of here because that's not within the range of sine inverse. It's going to be an angle that that still has the same sign, right? -1/2, but in a proper quadrant. So the sine inverse of -1/2, remember sine's defined from -pi/2 to pi/2, so that's going to be a negative angle, the one that complements the 11 pi 6, kind of like we saw in our example, part C. Okay, so instead of going all the way around this way, 11 pi 6, we're going to keep the negative pi 6, -1 pi over 6. So this is actually going to spit out -pi over 6, which is not the same, right? So we can't just assume, poof, cancel, right? The nice thing is that we can do that if it's this direction, but not if the inverse is on the outside. So if you want to take a stab at that one yourself, it's in the same kind of boat as this one. You can go ahead and pause and do that right now, real quick. So let's take a look at this one together. Well, the cosine of 5 pi 4, so this is going to be cosine of 5 pi over 4, is going to be 5 pi over 4 is in quadrant 3, so sine and cosine are both negative, so √2/2, negative. So this is the cosine inverse of -√2/2, but we need to stay within, remember cosine has to stay within 0 to pi, right? And within 0 to pi, what's going to spit out -√2/2 for cosine? We're going to have to be in quadrant 2, aren't we? So that's going to be pi 4 is 3 pi over 4. So actually, 3 pi over 4 is what would end up being spit out of here rather than 5 pi over 4. All right? I'm going to throw in a little bit of bonus content here to add on to something we've done before with solving trig equations. I want you to notice something here. I put two trig equations up, but they're actually very similar. This says 6 sine x then plus 1 equals 4. This says 6 sine that stuff plus 1 equals 4. In fact, I like to do this kind of covering up a little bit here. At this point, those two equations are essentially the same. So let's utilize this fact. You can go ahead and solve this one on your own just as a practice one real quick. But if we subtract 1, we get 3. So we get sine x, 6 sine x equals 3. And so sine x equals 3 over 6, which is 1/2. And then we can just think, oh, okay, well, what sine has a value of 1/2, right? Or you could think x equals sine inverse of 1/2. Or you could just undo it in your head already, whatever. But either way, what we get here is going to be pi over 6, I believe, right? Well, even though there's something weird in here, it's still okay, because we know this is still going to boil down to this equaling 1/2, right? So what I have here is sine of 2 parentheses x plus 1 equals, right? We minus the 3, subtract the 1 and divide by 6. That equals 1/2, which again means this business must equal pi over 6. So ignore the fact that it's not just x in there. It still means whatever's in there itself equals pi over 6. So I have 2, and then x plus 1 equals pi over 6. Now we just have a little bit more to do to solve for x, that's all. So if we divide by 2, pi 6 over 2 is pi 12ths. So I end up with x plus 1 equals pi over 12. And then subtract that, and I get pi 12ths minus 1. Or if you want, you could make it common denominator, so it'd be pi minus 12 all over 12. So this becomes x equals pi minus 12 all over 12. And that would be it. So there's a little bit extra to add on there to think about. And that's it for today, so happy math, and we'll catch you next time.